Hello everyone, my name's Logan, welcome back to the lecture hall. Today we're covering section 4.3, how derivatives affect the slope of the graph. Wow, that's a long section name. And this is going to just be the next lecture in our UCI Math 2A single variable calculus course. So, f prime of x represents the slope of the curve y equals f at the point x, comma f of x, right? And we all know this. The derivative, the first derivative, gives us the slope of our function. And then it states that if f prime of x is greater than 0 on an interval, then f is increasing on that interval. If f prime of x is less than 0 on an interval, then f is decreasing on that interval. So what we can do is we can use this to find intervals where the graph is increasing and decreasing, right? But where do we start? How do we figure that out? Well, first we need to find where f prime of x equals 0, otherwise known as we need to find the critical values of our function. What we can do is find the critical values and plug in numbers that are just greater and just less than the critical values and see if the intervals are positive or negative. But there is a note that not all critical values can be a local max or a local min. So, how do we figure out if there's a local max or a local min, or when there's none? Well, what we do is the first derivative test. So it states, suppose c is a critical value of a continuous function f. A, if f prime changes from positive to negative at c, then f has a local max at c. B, if f prime changes from negative to positive at c, then f has a local minimum at c. And then C, if f prime is positive on both sides of C or negative on both sides of C, then f has no local max or local min at C, at our critical value C. So now we know what f prime says about our function f, but what does f double prime say about f? Let's look at these two graphs. We see 1 and 2, right? And they both go from points A to B, except they're curved differently. And what do I mean by curved differently? Like this one is shaped like that, and then this one is shaped like this. Well, this brings about two definitions. And it states that if the graph of f lies above all of its tangent lines on an interval I, then it is concave upward on that interval I. If the graph of f lies below all of its tangent lines on an interval I, then it is concave downward on an interval I. And what do we mean by this? Well, if we were to just take tangent lines of our functions at every single point on our function, and we have a few hundred tangent lines, an infinite amount of tangent lines, we can see that here, all the tangent lines lie above our graph. They're all on top of our graph, you could say. And then what this is saying is this is going to be concave downward, right? Because our graph lies below all of the tangent lines. And here, it's the opposite. All of the tangent lines lie below our graph here, right? Because if you were to find the slope of them, they're all going to make lines like this. And this would be concave upward, right? So we can say this is concave down, this is concave up, and we get a little more insight about our graph. But how does that relate to our second derivative? We can use our second derivative to find where the graph is concave upward and concave downward. This states if f double prime of x, second derivative of f, is less than 0 for every x in the interval I, then the graph of the function is concave downward on the interval I. If f double prime of x is greater than 0 for every x in I, then the graph of the function is concave upward everywhere on I. Right? But then what if f double prime of x equals 0? It's kind of like the same thing as our first derivative test. We have our critical points. Well, we get a definition. A point P on the curve y equals f of x is called an inflection point if f is continuous and f changes from concave upward to concave downward or concave downward to concave upward, either one. So an inflection point is where the graph of the function, or the second derivative of the function equals 0 and the concavity changes. Now, for the last part of the lecture, we're seeing how the second derivative can help us figure out our maxes and mins as well. So, suppose f double prime is continuous near C. If f prime of C is equal to 0 and f double prime of C is greater than 0, then f has a local minimum at C. And then if f prime of C, the first derivative of f, equals 0, and the second derivative of f at C is less than 0, then f has a local maximum at C. So, as I am hoping you're seeing, that as our derivatives can help us give descriptions of our graph, and we can use them to figure out our critical points or inflection points that are important pieces on the graph to see the shape of our function. So this is all I wanted to cover in the lecture portion of the video. Let's transition to some practice problems. Alright, we're just going to do one question. We're going to do number 9. It says f of x is equal to x cubed minus 3x squared minus 9 plus 4. Find the intervals on which f is increasing or decreasing, and find the local max and mins. And finally, find the intervals of concave up and concave down. Okay, that's not too bad. So we know that to find where it's concave up and concave down, we have to use find the second derivative. So what we're going to do is we're just going to find our second derivative first. So we're going to find our first derivative and our second derivative. So if we have f of x equals x cubed minus 3x squared minus 9x plus 4, f prime of x is equal to 3x squared power rule minus 6x minus 9, which is equal to 3x squared minus 2x minus 3, and this is equal to 3 times x minus x plus 1 x minus 3. Okay, then if we were to do f double prime of x, we use power rule again, so that becomes 6x minus 6, which is equal to 6 times x minus 1. Okay, what will this give us? Well, we find where these are equal to 0, and we get some points. So we get f of prime of x equals 0 when x equals negative 1 and 3, and then f double prime of x equals 0 when x equals 1, right? So what does that tell us? That tells us we have an inflection point at x equals 1, and we have a local max or a local min at negative 1 and 3. But we need to use the second derivative test to find the local max and local min of negative 1 and 3. The second derivative test states that if f prime of c equals 0 and f double prime of c is greater than 0, then f has a local min, and if f prime of c equals 0 and f double prime of c is less than 0, then f has a local max at c. So let's just test it. We plug in x equals negative 1, so f double prime of negative 1, what is that equal to? That is equal to negative 1 times 6 minus 6, which is going to be equal to negative 12, right? And then we do f double prime of 3, and that's equal to 3 times 6, which is equal, minus 6, which is equal to 18 minus 6, which is equal to 12. Okay, well, what do we found? Well, we found that this is negative, and the second derivative test states that if the second derivative is less than 0, then f has a local max. So that means we get x equals -1 is a local max. And then if f is 3, or f of 3, we get a positive, we get x equals 3 is a local min. And then what we can do is, it says find the intervals of concave upward and concave downward, right? And wherever we have, it's going to be intervals. So it's between, it's going to be, for this, it's going to be between what is negative infinity and 1, and then 1 to positive infinity. So negative infinity to 1, not include, is going to be, well, what is it going to be? Is it going to be concave upward or concave downwards? Well, it is going to be concave downwards from negative infinity to 1 because we have a local max at -1, right? So the graph is going to look something like that at -1, and at 1 it's going to switch here, somewhere around there, right? And whenever we have a local max on one side, that means it is going to be concave, concave down on that side. So this is concave down. And then from 1 to infinity, it's going to be concave upward. Concave up, because, well, this goes from concave down, so then this 1 is an inflection point, so that means it's going to be concave up. It also has a local min, and a minimum has a graph that looks like that. So from about here to there, you know, to infinity, that's concave up, because you can see like the parabola going up. So now on to the final part. I did skip around a little. It says find the intervals on which f is increasing or decreasing, and we only need the first derivative for that. And we know our critical points are -1 and 3. So it states that it is increasing. We need to find between we need to find between infinity, negative infinity, and -1, -1 and 3, and 3 and infinity. We need to find if it's increasing, decreasing, or what. And we can do this from our first derivative. And if we get a number that is in between negative infinity and -1, if it's negative, it's decreasing. If it's positive, it's increasing. And we do that for each thing. So we'll just plug in f of -2, f prime of -2. And that is equal to 3 -2 squared minus 6 -2 minus 9. Okay, and we get 3 times 4 minus a -12, so plus 12 minus 9, and that's equal to 12 plus 12 minus 9 is going to be positive, right? It's going to be greater than 0, so we know that this is increasing. Now, you can kind of just say, oh, well, if it's increasing and then it goes from a local max to a local min, it has to be decreasing from here. But we should still check it. And how do we check it? Well, we can just do f of 0. And we get that is equal to 3, 0 squared minus 6 times 0 minus 9 equals -9, which is a negative. So we know it's decreasing from -1 to 3. And finally, we do 3 to infinity. We just plug in f of 4. It should be increasing anyways, because it goes from increasing to decreasing, so that it must switch back to increasing. But we still have to check, because it is not always the case that that happens. So we do f of 4, and we get that is equal to 3, 4 squared minus 6, 4 minus 9, and that is equal to 3 times 16 minus 24 minus 9. which is equal to 48 minus 24 minus 9, which is equal to just 24 minus 9, which is positive, right? So we know it's increasing from 3 to infinity. And this is how we do these problems. They're not entirely that hard. You just have to take the first derivative, take the second derivative, and then just start plugging in numbers. And you use your first derivative test and second derivative test, and these problems will go by very fast. So that is all I wanted to cover in this video. Again, my name was Logan. Thanks for watching. Have a great day.